Hello, everyone, and welcome to reInvent. My name is Matt Crocus, Senior Director of Software Engineering at Vonage. In this session, we're going to share two separate journeys of two different organizations, Vonage and Aspect Software, as we each transformed our own real-time communication platforms to the cloud by leveraging AWS. We will share with you not only the path we each took to AWS, but also how and why we transformed our platforms to the cloud, along with tips and tricks we hope will benefit you on your own journey. In the first half of the session, myself and Nahar Aurora, who is a staff engineer on my team, will share the journey of Vonage as we transformed our real-time communication platform from what was previously a very enterprise telco-like architecture to one which is now a cloud-native architecture built with many AWS services and more suitable for Vonage as a software-driven organization today. For the second half of the session, I'll turn the mic over to our friends from Aspect Software, Rachel Muller and Tom Tainer, both solution architects who will share a similar journey of their own organization. So let's get started with the journey Vonage went through to AWS with our Vonage Business Cloud platform. But before we start that journey, let's just quickly set some context around the specifics of the workload in AWS we will be discussing in this session. Similar only in complexity to the telephony infrastructure we see here, the workload of our Vonage Business Cloud provides a unified communication service to our customers. At its core, this means providing real-time voice, video, and messaging services across many different networks as well as endpoints. At the same time, our platform must support very compute-intensive operations, such as real-time media transcoding, as well as speech-to-text and text-to-speech conversions. Our platform must also support a very network-intensive application, specifically involving high levels of packets per second as necessary for any real-time audio and video processing. And if that wasn't enough, our platform is also very disk-intensive, where real-time call recordings must be performed at the very same time. And all of these capabilities must work together with low latency as needed for any real-time voice and video processing. These services must also be highly available as necessary to achieve 5 nines or more of uptime as required in our industry. And of course, these services must be highly secure to protect our customers as well as our organization. And of course, these services must provide a global service to support an international business. Like many of you in the audience today, I'm sure, our journey to AWS started out with a platform built mostly on top of on-premise infrastructure. As we grew, we started to leverage AWS mostly for compute and object storage resources in a hybrid cloud model. After many years of experience in AWS, we eventually made that lift and shift decision to take all of our infrastructure and move it to AWS. So great. We're done, right? Not even close. Although those steps were an important part of our journey, where it became real interesting is around what we discovered and what we did related to a redesign once we had moved all of our infrastructure to the cloud. And what we found was that we were in AWS. We were not designed for AWS. This is a very important distinction and something that can be very difficult for many companies, not only to realize, but also to address properly from a long-term strategic technical direction. At Vonage, not only do we recognize that our platform, which had served us so well for so many years, was no longer the best suited platform for our future ambitions, we also decided to do something about it. We invested a large amount of time and effort to transform our platform based on technology decisions of today, not those of a prior decade. Once we had lifted and shifted our platform as a whole to AWS, we were still left with the same monolithic application that had prevented us from taking advantage of many of the rich services in AWS. This monolithic application was still running on very rigid infrastructure on AWS, as odd as that might sound, where we had thousands of instances running 24/7, 365 days of the year with very low overall resource usage. We were also still managing application and data services and relearning the operational expertise to maintain those systems in a cloud environment, none of which helped to differentiate our service to our customers. And of course, with a large monolithic application, you can imagine the typical long release cycles that came with it, where software releases often involve timeframes on the order of months, often with that unpleasant associated rollback scenario. From a call processing perspective, our applications and call flows were mostly designed around an active standby model, which simply translated to much waste in AWS. We would often look at the charts and make the obvious conclusion that we should really follow our load curve with autoscaling, especially on our call processing infrastructure. You know what? But getting there was always more than an arm's reach away for us. Our platform also had several dependencies on a primary region, which, although it was highly available, it left us without the ability to exit a region quickly and easily in case of a service disruption of any kind in our primary region. All of this meant that we were focusing more on engineering and less on innovating. For many of these reasons, we asked ourselves, should we redesign? Specifically redesign our platform for a cloud environment. Some would argue this was just too big. Others would argue this was a unique opportunity. An important point to remember in your journey is that redesigning your platform natively for the cloud does not necessarily mean rebuilding your platform as a whole. Of course, you can and will rewrite some components from scratch. Redesigning your platform does not and should not necessarily mean starting over. At Vonage, we took this opportunity to leverage open source technologies that were more mature today than they were when our platform was initially built. We also took the opportunity to natively leverage many AWS services, such as AWS, such as RDS, Elasticache, Lambda, step functions, and more. We leveraged them natively within our platform. And we'll talk more about these in more detail. We also decided to make infrastructure automation an integral part of our platform, something that our DevOps teams would build, deploy, and maintain in the same way they do their application code. So yes, we decided it was time to upgrade, and not just upgrade an application or a tool, but to upgrade the platform as a whole and bring it to the cloud. This is where our journey also became a cultural shift for Vonage. Not only would we be upgrading our platform, we would be upskilling our teams, enhancing our processes, and most importantly, creating better business outcomes for our customers. Taking the leap on this journey first involves seeing the big picture of where we wanted to be. Not just a few weeks or a few months into the future, but where we wanted to be 1 to 2 years ahead, and then starting a small team with a mandate to execute on this big picture. For this phase of the journey, we started small with a team of just a few, and we grew that team over the course of a year. Within 2 years, we had redesigned our platform and successfully migrated our customer base to this new platform. We had made a heavy investment in automation, and we chose to fail fast so that we can make pivots early, which we did many times. Prior to working at Vonage, I myself had been involved in many startups, some going back to the dot-com boom of the 90s. This effort within Vonage had all the excitement, energy, and technical innovation that goes into a startup. This is, in fact, the culture that Vonage itself was founded upon, and we were essentially going back to our roots to transform ourselves and once again be a technology disruptor in our efforts. So today, our Vonage Business Cloud platform has had a heavy investment in automation. We mostly use Ansible, where we leverage integration with AWS SDK very heavily to make our automation do things that we simply could never do before within our own data centers. We treat our infrastructure like code because it is written and it is maintained by our developers, the same ones which write the applications which leverage the infrastructure. We now have automation in place where rebuilding all environments from scratch occurs frequently, daily in dev and weekly in QA and production. We leverage blue-green deployments, which allow us to rebuild even our production environment while we have live calls on it, without having to perform failover maneuvers. We can do this because our automation and our applications work together to provide a platform which is now cloud native. We also now have CI and CD using code pipeline and code deploy, where we can now deploy multiple changes a day and move those changes through our environments with a simple click of a button. We now push out changes to some of the most critical components of our real-time communication platform through code pipeline and code deploy, which include routing logic to our SIP registrars and SIP proxies, as well as dial plan logic for our real-time communication application servers, as well as software for many of our microservices. All of this automation allows us to now innovate at a very rapid pace. Today, our Vonage Business Cloud platform has a very dynamic and elastic infrastructure. We use auto-scaling groups with EC2 and CloudWatch such that our infrastructure scales out horizontally to match demand and scales in when demand decreases. To support auto-scaling on components of our infrastructure, which process voice and video calls, this means we had to treat our infrastructure as disposable from day one. This means any file written to disk, whether it was a call recording or a call detail record, needed to be uploaded to S3, since that instance could scale away. We also now use serverless Lambda functions for processing every call event on our platform. This means every telephony event, such as a call is ringing, a call is alerting, a call is answered, or a call is terminated. Each and every one of these events needs to be processed and consumed by other parts of our platform to maintain dashboards and features which rely on these events. On our real-time call processing infrastructure, whenever one of these events occur, we simply invoke a short-lived Lambda function and process these events in a serverless piece of code which is highly elastic with zero maintenance. You can imagine the timing of these events are very critical, And with Lambda, we have been able to easily scale to well over 6,000 lambdas a second during peak periods of our traffic. For some existing applications where maybe an object store such as S3 is not feasible, we have been able to leverage EFS and have a highly elastic file system, which simply grows as our demand increases. There's no more managing NFS infrastructure ourselves. Today, our Vonage Business Cloud platform is designed such that even our call flows take advantage of not only a multi-AZ architecture, where calls are processed in clusters which are active across multiple AZs within a region, but these call flows also know how to fail over automatically to another region, which is active as well for customers. With auto-scaling, if and when a cross-region event or need occurs, auto-scaling, the capacity of one region will simply scale up to meet the increased demand from the other. Of course, we also leverage many AWS managed services, such as RDS, Elasticache, Lambda, and others, which are also highly available within a region themselves. When building an HA platform which leverages services such as these, you'll want to make sure you have an operational button to quickly and exit a region, literally with a simple yet secure button. Failures won't always be black and white. There can be gray types of failures. And for these reasons, you want to make sure you have that operational button to exit a region for any of those gray failures, in addition to having automatic failover, of course. Today, our Vonage Business Cloud platform leverages many managed services in AWS. By redesigning our platform for AWS, we were able to natively leverage many services that previously required much time and effort to manage ourselves. As an example, we now use RDS for all of our relational database needs, such as account data and usage data. We also leverage DynamoDB for microservices which need to manage global state, such as the state of an agent in a call queue. For distributed real-time caching, such as that needed to manage the state of a call, we rely on Elasticache Redis. We also rely on Elasticache Memcache for managing real-time transient registration events. We pump all of our call detail records into a Kinesis stream, which our mediation system uses to process those records and perform mediation prior to rating. As the usage on our platform grows, we simply add more shards through automation to our Kinesis streams to get more throughput. It's that simple. Since our infrastructure is very elastic and we try to optimize keeping as much data as close to our call processing components as possible, we leverage SNS to decouple the job of publishing account changes out to our infrastructure. We also use SQS to distribute our microservices across our elastic infrastructure for jobs such as transcoding call recordings, converting documents for fax transmissions, and storing voicemail recordings into long-term storage, as well as many other use cases. And of course, all of these services, including the creation and discovery of these services, are baked into our automation so that a single button can be used to provision everything needed for an environment. Invest in automating everything. The return on investment here is a game changer, and the programmability of AWS is a key differentiator as compared to legacy practices still used by many others. Today, our Vonage Business Cloud platform is running its workload in AWS and providing a high-quality, low-latency service. In order to achieve, we use EC2 instances with EBS volumes for all of our signaling and media processing components. We have found that the C5 instance type with the enhanced networking adapter provides the best throughput, specifically in terms of packets per second, with extremely low latency, which is critical for any real-time communication platform. In order to ensure a high quality of service, we invested efforts in fast auto-scaling techniques to make sure that our call processing infrastructure instances can be launched and brought into service within minutes. This is necessary to ensure that our platform can take any punch which comes its way and still maintain high levels of quality. Kernel tuning. This is something that just goes with the territory with any real-time communication platform. We have found that tuning the clock source and the scheduler of the kernel are important factors towards maintaining high quality and low latency. You want to make sure that you profile your kernel not just under load test environments, but also under production workloads where possible. I'm now going to let Nahar share some tips and tricks we learned on our journey. Nahar?
Thanks, Matt. Hello, everyone. Super excited to be here and to be able to share some of our learnings with you all. We hope that some of what we've gone through and learned is useful for you as well. Now, one of the very first things that we need to be concerned about is the speed with which our ASGs can keep up with traffic patterns. As Matt mentioned, we use ASGs extensively to scale out our infrastructure horizontally and to keep up with demand. In order to do that, instances need to come up quick and put themselves into service fairly quick to avoid potential scaling issues. Incoming call and media processors, for example, must be ready and willing to take on traffic to avoid call quality issues caused by existing instances going too dense. To achieve this, one of the things that we do during cluster deployments is to package up and put into S3 the right version of our automation code. And then at launch, new instances pull down this automation and do a partial local run to configure themselves as fast as they can. This avoids remote execution overhead and also keeps things local. This also leads into our next point, which is to, as much as possible, only have configuration on instance launch. This way, we can respond within minutes to spikes in traffic. We pre-build our AMIs with packages installed, build steps already performed, and so on. This front-loading ensures that the call processing system is resilient to outages, such as repositories being down or packages getting removed. We basically want to get as close to zero external dependencies at launch as possible. This avoids instances coming into service, but not being in a state to service requests. We also specifically designed to handle failures, address breaking points within the system, and to avoid service disruptions. A big part of being in the cloud is to anticipate and address failures during normal operations. This may not happen a lot, but when they happen, they should not cause outages. For example, let's say an underlying disk fails and the volume goes into read-only mode. Part of our automation is to detect such routine failures before they happen and then remove the need for manual intervention. All ASG instances have an application and instance-specific health check running, which looks for things like services being up, interfaces being healthy, disks being healthy, and so on. And these checks happen once every minute. And if an instance is deemed unhealthy, it's marked as unhealthy in the ASG. Now, this does not mean we can terminate instances at will. Instance lifecycle still needs to be managed. We also have fail-safes in our logic to not scale away all instances in the ASG due to systemic issues. We must handle terminations gracefully. When an instance moves into terminating wait state for any reason, could be unhealthy, part of normal scaling at night, we make sure that we don't scale away suddenly with checks specific to the application role. We allow instances to drain traffic gracefully. If we've got any calls up, we wait for the sessions to end. For example, in the picture there, on our media processors, if we have a local data that's still being uploaded, for example, call recordings, voicemails, CDRs, we wait for those to finish processing as well. Once all the data and sessions are cleanly drained off, then we let the termination proceed. Performance obviously is not for free just because we're in the cloud. You still need to do all your homework for performance tuning, go through that cycle of tuning, testing, applying what you learn multiple times. Tuning is application specific. For example, instance sizes vary, instance types vary, system optimizations vary, all based on application and workload type. I won't dig in too much here, but there's a great deep dive on performance tuning EC2 instances that you should totally check out, whether it's live or on the web. From a kernel tuning perspective, we went with the TSC clock source, which is an optimization specific to applications that invoke get time of day system calls a lot, and one that AWS recommends you apply as well. This had a big impact on our get time of day performance, which impacted latency on call flows for us positively. And internal analysis saw a difference of 270 seconds versus 21 seconds for 1 million calls to get time of day between the Zen clock source versus the TSC clock source. We also went from a 250 Hertz timer on a stock Debian AMI kernel to a 1000 Hertz timer to get better resolution and improve latency on the scheduler. This is a recommended mitigation to avoid choppy audio issues on slower clocks for call and media processors. For network tuning, we went with C5 instance sizes for media and signal processing instances to improve packets per second using the right instance size. Now, instance selection is obviously very important. Not all applications should be on the same instance sizes. Call and media processors, like I said, are on C5 2x largest for PPS, but our provisioning applications, which don't need to push as much in terms of networking, are on C4 2x largest. We leverage lambdas and step functions extensively. Here, I'll just touch on a couple of optimizations we've made for our lambda usage. By the way, Amazon has a great resource for digging into best practices on on lambdas listed at the bottom of the slide there. You should check that out. Be mindful of overhead. Invocation can overshadow execution time, especially for smaller lambdas. So avoid the temptation of making your lambdas too tiny and fragmented. The right granularity has a big impact, especially for low latency fire and forget events. For 3 chained lambdas in our call state application, for example, simply merging them into one lambda invocation dropped our total execution time from 70 milliseconds to 20 milliseconds. Another thing to keep in mind, again, very important for low latency lambdas, is reuse. Reusing resources such as database and cache connections across lambda invocations by making them global in the execution context had a big performance impact, and something Amazon recommends you do as well for a performance boost. It was especially relevant for lambdas that have a large number of invocations. The last thing that I want to touch on with respect to lambdas is isolation. For call state events, we have about 500 million invocations on weekdays, which is roughly like 6,000 per second at peak. We move these lambdas into their own subnets for network segmentation. This avoids impacting other services. For example, when we have spikes in call volume, the call state application could take up all the IPs in that subnet and cause other applications to fail. This also avoids impact from other services. Like a rogue lambda could chew through all your IPs in that subnet and cause call state applications to fail. Amazon recommends going with dedicated lambda subnets, which is what we did. If that's not possible in your setup, you can do VPCs as well, but do something. Using reserved concurrency helps, but without network level isolation, it's just an outage waiting to happen. Another important principle for us is localization of call flows. This helps us with both reducing latencies and avoiding failures during calls. We try to stay within region as much as possible. In the picture there, you see Virginia on top, Oregon on the bottom, and the same application stack and call flow. We also optimize to stay within AZs for media and signal processing to avoid inter-AZ networking issues. All data needed by call processing is provisioned to caches locally when possible. For example, local instance memcache or Redis, or to a within region elastic cache cluster, which acts as a global cache in that region. There is also an in-region RDS cluster for persistent data, as well as an S3 layer for provisioning objects such as recordings, voicemails, user profiles, and so on. And the provisioning system ensures that all this data needed in that region by the call processing system is available in that region. At times, your applications will need region awareness. Some applications need a global view. For example, we've got a call state dashboard that needs to know the state of calls across all regions. Others need region awareness for data that needs to be written to or read from multiple or specific regions. The mediation system, which is shown here, is an example of that. Call processors, as they're writing records, they push them up to an S3 bucket within that region, which triggers a lambda that then pushes these to a Kinesis stream, off of which the mediation application is picking up records, and then pushing those mediated records to a specific database primary in a specific region. This follows a pattern of staying within region as much as possible and going across region only when needed. This is a key principle for us for applications that need region awareness or that need to access global data or go across regions. We delay region awareness to be as late in our processing chain as possible, this way avoiding cross-region dependencies. The final trick that I want to touch on is a pattern that we've seen occur repeatedly in the evolution of our system and which has worked out very well for us. It's a standard pattern we use for performance, decoupling, resilience, and to distribute work across services. We use a combination of S3, SNS, and SQS to avoid processing tasks during call flows. CDRs, voicemails, call recordings, transcription flows, these are all examples of that use this pattern. In the picture there, you're seeing the voicemail flow here, where as messages are being recorded, they're left locally on the call processors on EBS volumes. These files are then pushed up to S3 via microservices outside of the call flow, which then triggers consumers of SNS and SQS to pick up these files, apply processing on them, transcription, transcoding, and so on, and then push them towards the voicemail cluster at the end. I hope you guys found this helpful, and now I'm going to hand back over to Matt.
Thanks, Nahar. And thank you, everyone, for letting Vonage share our journey to AWS. I'm now going to hand the mic back over to Rachel and Tom from Aspect Software so they can share their journey to AWS.
Thanks, Matt. My colleague, Tom Tenner, and I are going to spend the rest of this session talking about how we transformed a single-tenant, low-latency chat service into a software-as-a-service component. But first, I'm going to go into a little background about what we do at Aspect Software and a brief history of our moving our components to the cloud. And then Tom's going to come over and talk about that chat service and the software-as-a-service component that replaced it. And then I'll return to go over some lessons learned during the transformation process. And then Tom will finish up with some final takeaways. At Aspect Software, we build what's called customer engagement services. So what does that mean? Well, if you've used your landline or your mobile phone to talk to a live person about your bank account or a support issue, or you've interacted with a chatbot that helps you find the perfect wine for your next dinner party, or you've gotten a notification on your mobile device about an upcoming doctor, dentist, or haircut appointment, then chances are you've interacted with customer engagement services from Aspect Software. We've spent the last almost 3 years now taking a product suite that used to work primarily in our customers' data centers and re-architecting it as a software-as-a-service offering in the cloud. And we call that software-as-a-service offering Aspect Via. This slide illustrates the re-architecture effort as of last year when Tom and I presented at reInvent. At this time, you can see we had a number of services running in the cloud. We were just starting to take advantage of serverless Lambda functions. We were already well on our way to using managed services such as Redis and S3. And there was still one part of our product that wasn't running in the cloud, specifically our media servers, which bring audio into and out of Aspect Via. Those were running in Aspect hosted data centers. Fast forward a year, and the major enhancement now is that those media servers are in the cloud as well with everything else. We're also taking advantage of more managed services such as Kinesis. We're also leveraging containers. And this allows us to skip the install process during the deployments, thus reducing delivery times. But the re-architecture effort wasn't just focused on reducing delivery times. We really wanted to take any single-tenant, low-scale services we had and re-architect them as software as a service. But we had users on our platform. So we needed some guiding principles to make sure that our users had a smooth transition during this time. So the number one priority was that our customers and our customers' customers continued to have consistent behavior from Aspect Via as we refactored in the cloud. Secondly, we wanted to make sure we were continuing to use managed services and serverless technologies where it made sense, so that we weren't bogged down with deployment tasks, and we could focus on accelerating our transformation and innovating as well. And lastly, we wanted to build an API for 2 reasons. One was so that our customers could control and program Aspect Via to better integrate with their business processes, but also to provide an abstraction layer during this transformation process to protect the clients against any refactoring that was going on. As we transformed the first set of components, we realized there was a pattern emerging, and we called it the migration pattern. This slide illustrates the phases of the migration pattern because typically our transformations were taking multiple development cycles. Here we have it. The example is a voicemail service that we completed our architecture effort on earlier this year. It's a very basic service. It does what you think. You can retrieve your voicemails, you can play back your voicemails, you can delete them, you can forward them, etc. And in the beginning, it only communicated with internal clients, and it then communicated with an RDS instance. The first phase of the migration pattern was to build a new API. And again, this allowed external clients to now communicate with that original voicemail web service. It also allowed us to introduce the API gateway and the Lambda function in front of that web service. The Lambda's function here, called the redirect Lambda, was basically to translate from the new API to the old API. And at this time, the internal clients were still communicating with that original web service. Next, we introduced a microservice, which does everything that the original voicemail service did, except for that it can scale and is multi-tenant, and also communicates on the new API. At this time, we could remove that redirect lambda from the architecture. But the internal clients are still communicating with the original voicemail web service at this time. And so we have the old component and the new component both running in the architecture. And we call this the side-by-side stage of the migration. The last phase was to take the internal clients and have them communicate on the new API. This allowed us to remove the voicemail web service and complete the migration. Now Tom's going to come in and talk about how we did the chat SMS service transformation using these concepts.
Thank you, Rachel. This is the latest migration process that we did have, and we'll look at this legacy service that we had. This diagram shows the chat and SMS legacy service that gives customers non-voice media channels like chat and SMS that they can provide to their customers. This is a single-tenant on-premise solution that supports the click-to-chat buttons that you'd find on many customer websites. When a chat or SMS message arrives, a session is created, stored in memory, and the message is forwarded on to the self-service component or to an agent in the contact center. We also support HA for this solution, and we do that with active-active and active standby models. And we have a number of strategies to deal with failures to make sure that those chat messages get through when they need to. But what this architecture is it's not scalable. It's a single tenant solution. There's a fixed hardware profile that supports a maximum number of chat and SMS sessions. The resources for this solution sit in a data center 24/7, 365, waiting to service the maximum number of simultaneous sessions. Much of the time, those resources sit idle or lightly used, really costing more money than they're making. This legacy architecture also requires a number of people in order to manage the hardware, the software, and the related updates. Enter our new SaaS architecture, our Omnichannel messaging service. This is the new messaging architecture that we deploy in AWS that leverages serverless and managed services. We call it the Omnichannel messaging service because it delivers the same legacy web chat and SMS messaging, but it also introduces new messaging frameworks like Facebook Chat, Slack, and many others. All external communication for this system takes place through API Gateway, including the Omnichannel messaging. It allows Aspect to scale, throttle, secure, and monitor our APIs. And when we need to deliver the unsolicited messages, if we go back up into the upper left quadrant there, we have the web chat implementation. And that is a little different than the other messaging frameworks because we have to deliver unsolicited messages to the browser-based web clients. And in the legacy system, we used to use WebSockets to deliver those messages. But WebSockets are not available in API Gateway, so we had to develop our own long polling solution similar to what's available in Amazon's SQS. And this is something Rachel's going to talk about in more detail. So here's an example of an SMS message flowing in through the system and being delivered to self-service on the other end. The first thing that it reaches is Amazon's API Gateway, which invokes our first Lambda that validates and transforms the SMS message and places it on a Kinesis data stream. The second Lambda is the heart of our messaging system. It's the messaging manager, and it consumes the Kinesis events. It will create and manage a session for that customer interaction. It will record and maintain a transcript of all the messages sent back and forth, and then it will route events. And in this case, it routes the events to self-service. Self-service receives the message and determines how to handle the customer interaction. An example is the wine box that Rachel talked about before that makes beverage suggestions based on the meal that was described in previous messages. And sometimes the right response for the customer is to offer to transfer them to an agent in the contact center, which it can do. So once it finds the response that it wants to send back, the message takes a similar path back to the mobile device. Now, we've looked at two different Lambda functions, and they transform and route events. Just as Nehar said, we use the Amazon Lambda best practices in their documentation as kind of a checklist to make sure that we're writing Lambda functions that are the most efficient, that have the shortest startup time and don't have any delays, so we can get the fastest performance out of these. Our third Lambda function, the last one that we're going to look at, is the transcript Lambda. And that's responsible for wrapping up a customer interaction and saving the transcript and other information to S3. And then it sends a message to our quality management component, which then where the interaction can be evaluated and scored. Now, we heavily use Elasticache Redis for storing sessions, for storing other information, and our web chat clients also get Redis queues that are used for long polling. We deploy a Elasticache Redis cluster with cluster mode enabled. We have at least 3 shards in the cluster, and each shard has 3 replicas that are distributed across availability zones, and we turn on automatic failover as well. Kinesis Data Streams, another managed service that we use heavily. We like that for its guaranteed message ordering, for its durability and scalability. We also use Firehose so we can persist events to S3 for auditing and for playback in some cases. And for web chat clients that are supporting long polling, we tried using Lambdas at one point and found that wasn't the most efficient. So we pivoted on that and developed a new service that's a Java-based service that's hosted in Kubernetes that's able to scale up and meet the long polling needs much better. So some of the key wins that we've had with the scalable cloud architecture, these are some of them. And we've been able to support a lot more customers for a lower cost and with a reduced operations responsibility. This is due to embracing the different managed services such as API Gateway, Lambdas, Kinesis Data Streams, and Elasticache Redis. Now I'll turn it over to Rachel, and she'll talk about lessons learned with Lambda and long polling.
Thanks. Thanks, Tom. That's a lot of L's. So I am going to talk about some things we learned during the transformation process, but only focusing on a small part of the architecture because it's quite large, as you saw. Specifically, I'm going to talk about the part of the architecture where the web chat clients retrieve messages from the message queue. And this is an interesting part of the architecture because we iterated through a number of designs over a number of development cycles. Now, the first design we considered was to use SQS FIFO to hold the messages. For those that aren't familiar, SQS is a messaging service, but the FIFO part guarantees message order, and this is something we required for the design. Now, SQS also supports long polling natively, so we thought, well, it'd be simplest to have the web chat clients communicate directly with SQS. We soon found out, though, that it was really hard to figure out how to authorize the request from the web chat clients in a consistent manner with the way we authorize requests in the rest of the system. Also, we didn't have a lot of control over the rate of requests to the web chat client. So we quickly moved on from this design and actually didn't take it into production. The next design involved adding an API endpoint. You can see it here, /streaming/events, for the web chat client to use. And now we have the API gateway and a Lambda function in front of the SQS service. And the Lambda is there because you can't send requests for long polling directly from API gateway to SQS. And now we had authorization and a throttling mechanism because those are native features of the API gateway. And we really liked this design. However, we went into a region where we found out that SQS FIFO was not available. So we had to move on from this design. The next design involved replacing SQS FIFO with Redis queues. And for those that aren't familiar, Redis is not just about caching. You can also build message queues, and those messages have guaranteed message order. So again, a good fit for this design. The thing about Redis, though, is that it has to be deployed in a VPC. And this added a new dynamic to our design. Specifically, it meant that the Lambda now had to interact with the VPC. And therefore, we needed to have subnets and IP ranges for the Lambda invocations to use. Now, the nature of long polling is such that the Lambda, an individual invocation, could take many seconds to come back, especially if there were no messages in the queue. And the long polling times out. And in the worst case, you have hundreds, if not thousands, of web chat clients. Long polling, you may have hundreds, if not thousands, of Lambda invocations all waiting for messages and running many seconds. And so you need lots of IP addresses to support that. At the time, we didn't have the ability to dynamically scale our subnets up and down. So we were really forced to deploy for the worst case that we could think of. Compounding matters was that in the early load testing of this design, we ran up against the AWS account limits for the maximum number of simultaneously running Lambda invocations. And while it was easy to ask Amazon to raise those limits, we realized that this design had a number of weaknesses, and that really long polling is not a good use case for Lambdas. Lambdas should run very short periods of time, respond in sub-second timeframes to really be most effective. So we moved on from this design. Where we're at right now is that we've replaced those Lambda functions with long-running web services. And those web services run in containers, and the containers are scaled up and down dynamically using an orchestration service, specifically Kubernetes. Now we've freed ourselves from worrying about the IP addresses being available, and we also don't have the account limits for the Lambda invocations to worry about. And even though we did iterate through a number of designs before we settled on the technologies that best suited our needs, we had the API, the streaming events API endpoint, to help us to protect our clients during this time. So the system behaved just as it always did, even though we were refactoring the design. And it was actually pretty easy to move from one design to the other because it mostly involved replacing one managed service for another. Now I'm going to hand it back over to Tom, and he's going to give you some final takeaways.
So we've worked hard with our designs and our development processes to transform the product incrementally without any abrupt monumental changes. APIs shield our customers from the internal transformations in anything going on with our products. And we try to embrace agility. When something doesn't work, how can we change it? If new services are introduced by Amazon or the industry or the open source community, how can we take advantage of those? Just last week, AWS Lambda announced that they support the new enhanced fan-out with HTTP2 for Kinesis data streams. That's something that we're going to look at carefully and see how we can include into our product. And who knows what other features and services Amazon may announce this week that will benefit us. And lastly, we're fortunate to have enterprise support and the experts that comes with. And we thank the team for helping us. They help us with a number of different things, but the big thing is the expertise. When they can't answer the questions, they're quick to set us up with subject matter experts throughout AWS that can help us with our direction. Thank you very much. I think I have to tell you contractually that I can't entice you with anything, but that please fill out your surveys. And last year, I think if you filled out enough of them, you were able to pick up more swag. So maybe that's a reason to do that. So thank you from Aspect and Vonage.